Force and pressure. Lesson preview. Force, a pull or a push. Types of forces. Resultant force. Effects of force. Pressure and its unit. Pressure exerted by liquids and gases. Atmospheric pressure. If you look around, you will see many things moving. Some move slowly and some move fast. A rolling ball may suddenly change its direction. Have you ever wondered what causes these changes? A body cannot start moving or stop moving, change its direction, or shape on its own. It can perform these functions only when force is applied to the body. Let us learn more about force. Force, a pull or a push. We use force to perform various day-to-day activities. When we pull or push an object, it moves. We need force to move objects. Pull and push are forces. A pull or push acting on an object is called force. Force is usually denoted by the letter F. The standard unit of force is called Newton, denoted by N. Force does not always move an object. For example, you can push a wall without displacing it from its position. Push and pull forces make things move. Let us understand force with examples. Force as a push. When an object is moving away from the point of application of force. Pushing a door to open it. A lady pushing a pram. A vegetable vendor pushing a vegetable cart. A boy kicking a football. Force as a pull. When an object is moving towards the point of application of force. A horse exerts a pull to move a tonga. Pulling a door to open it. Drawing a bucket of water from a well. Opening the drawer of a table. Forces are due to the interaction of objects. We have seen that when force is applied, either push or pull, there is some kind of change in the state of motion of the object. Let us see when force comes into play. Suppose there is a car which is not starting. Now if you stand behind the stationary car, it will certainly not move. A man standing behind a stationary car. A man pushing a car. Now if you push the car, that is to say, force is applied, it will begin to move in the direction of applied force. When we kick a ball or pull a cart, interaction of two objects is required. A boy kicking a ball. A cart being pulled by oxen. Thus, we can infer that at least two objects must interact for a force to come into play. We can therefore say that forces are due to the interaction of one object with another. In most cases, like kicking a ball, pushing a cart, pulling a drawer, the force and the object come in direct physical contact with each other. Such forces are called contact forces. However, sometimes interaction may not always involve a direct physical contact. Such forces are called non-contact forces. For example, a magnet attracts iron objects without coming in direct contact with them. Types of forces. There are thus two kinds of forces: contact forces, non-contact forces. Contact forces. Forces that act on objects by direct physical contact are called contact forces. The following are some kinds of contact forces. 1. Muscular force. The force exerted by the action of muscles in our body is called muscular force. Examples: when we lift a bucket of water, push a cart, kick a ball, walk or run, we use muscular force. Digestion of food, bending of our body, and breathing are all carried out due to the force exerted by the muscles. Examples of muscular force. Similarly, animals like bullocks, horses, donkeys, and camels also use muscular force to do heavy work such as pulling a cart, plowing, carrying heavy load, etc. 2. Friction. Friction is also a type of contact force. The force acting between two surfaces in contact with each other, which opposes the motion of one body over the other, is called friction or force of friction. The force of friction always acts on all moving objects and its direction is always opposite to the direction of motion. Example: A rolling ball comes to rest after some time due to the friction between the ground and the surface of the ball. A bicycle stops after some time if you stop pedaling, because of the friction between the road and the tires. Non-contact forces. Forces that do not need physical contact with the object on which they are acting are called non-contact forces. Magnetic force, electrostatic force, and gravitational force are examples of non-contact forces. 1. Magnetic force. Activity. Bring a magnet near iron nails. What happens? Bring two magnets with like poles near each other. What do you observe? Now bring two magnets with unlike poles near each other. What do you observe? You will observe that a magnet attracts iron nails even though it is not in direct contact with them. A magnet attracts another magnet when unlike poles are brought near, and repels another magnet when like poles are brought together. This activity shows that a magnet exerts force on another magnet without being in contact with it. The force exerted by the magnet is called magnetic force. 2. Electrostatic force. The comb acquires an electrostatic charge after it has been rubbed on the hair. The force exerted by a charged body on another body is called electrostatic force. This force also comes into play when the two bodies are not in contact with each other. Activity. Take a plastic comb. Rub it on your dry hair several times. Bring it near small pieces of paper. What happens? The pieces of paper will attract towards the comb. 3. Gravitational force. Every object in the universe, irrespective of its size, exerts a force on every other object. This force is known as the gravitational force. Gravity is the force with which the earth pulls everything towards itself. Examples: when a ball slips from your hand, it falls down. Fruits and leaves fall on the ground. Water in river flows downwards, and all objects fall down towards the earth. All these actions happen due to the force of gravity. Force of gravity. Resultant force. At times, more than one force acts on a body at the same time. In such a case, the effect on the object is due to the resultant force or net force acting on it. Activity. Take a heavy object like a table. First try to push it alone. Then ask one of your friends to help you push it. Is it easier to do so? Now if your friend pushes the table from the opposite end, does it move? And if so, in which direction? When both you and your friend move the table in the same direction, it can be moved easier and faster than when you had to do it alone. In the second case, table will move in the direction in which more force is applied. Thus, we can conclude that when two forces act in the same direction along the same line, the resultant force is equal to the sum of the two forces. When two forces act on an object in opposite directions along the same line, the net force acting on it is the difference between the two forces. You must have seen a game of tug-of-war. When the two sides pull the rope hard, at times, it does not move in any direction. This is because the resultant force, net force, acting on it is zero. If the direction or the magnitude of the applied force changes, its effect also changes. Effects of force. 1. A force can change the state of motion or rest. When you kick a ball at rest, it moves. In other words, force can make a stationary body move. Suppose a ball is moving on the ground slowly. If you push the ball while it is still rolling, what do you observe? Its speed increases. This shows that a force can increase the speed of a moving object. If you catch the ball, it stops moving. Therefore, we can say that force can stop a moving body. A bicycle can be slowed down or stopped by applying brakes. Force can decrease the speed of a moving object. We can conclude from the above examples that if the force applied on the object is in the direction of its motion, the speed of the object increases. If the force applied on the object is in the direction opposite to the direction of its motion, the speed of the object decreases. 2. A force can change the direction of motion of a moving object. Let us understand this with the help of examples. Examples. 1. A football player kicks the ball in a different direction. 2. A batsman hits the ball bowled at him. 3. A badminton player hits the shuttlecock either softly or smashes on the other side of the court. Thus, a force may bring a change in the state of motion of an object. State of motion means the speed and direction of motion. The two states of motion are at rest and in motion. At times, you may apply force but it does not result in a change in the state of motion of the object. You will not be able to move a big wall, irrespective of the amount of force you apply. Activity 1. Take plasticine or dough. Press it down with your hand. 2. Take a rubber band and stretch it. 3. Squeeze toothpaste out of a tube. 4. Press an inflated air pillow. 5. Pull a spring. What do you observe? Is there any change in size, shape or both? Note down your observations. Table. Description of activity. Change in size/shape. 1. Pressing plasticine or dough. Yes. 2. Stretching a rubber band. Yes. 3. Squeezing toothpaste out of the tube. Yes. 4. Pressing an inflated air pillow. Yes. 5. Pulling a spring. Yes. Can you add some more examples to this list? 3. A force can change the size and shape of an object. In all the above examples, we see that when force is applied on an object, its size and shape changes. We can thus conclude that force can move an object at rest. Force can make a moving object move faster. Force can slow down a moving object. Force can stop a moving object. Force can change the direction of a moving object. Force can change the shape and size of an object. Pressure. The force acting on a unit area of surface is called pressure. Pressure equals force, area on which it acts, equals force in N, area in M2. You must have experienced that cutting a fruit with a sharp knife is easier than cutting it with a blunt knife. This is due to effect of force in respect to the area it acts on. In other words, it is the amount of pressure that comes into play. This shows that pressure exerted is inversely proportional to the area of contact, i.e. the pressure produced is less if the area over which force is exerted is large. Decreasing the area over which a particular force is exerted increases the pressure produced. The area of the pointed end of a drawing pin is much smaller than its head. Therefore, when we apply force on the head, needle is inserted into the cardboard. Similarly, it is easier to cut fruits with a sharp knife because the area of contact of sharp knife is much less than that of a blunt knife. This also explains why a camel is able to walk easily on sand as it has flat, broad feet, or why potters or persons lifting heavy loads place a turban, round piece of cloth, on their head before placing heavy loads. The turban increases the surface area of contact of the load with their head. This in turn reduces the pressure on the head. Unit of pressure. In the SI system, the unit of pressure is Newton/meter2 or N/m2. In common use, this unit is called Pascal, Pa. It is named after the French scientist Blaise Pascal. 1 Pascal equals 1 N/m2. Let us now see an example where we need to calculate the pressure exerted by a force on a surface. Example: calculate the pressure exerted by a brick on the soil, if it applies a force of 5 N when A. It is placed upright on the ground. B. It is placed on its widest base. The dimensions of the brick are 25 cm L times 10 cm W times 5 centimeters h. Solution A. When the brick is placed upright, area of contact with soil equals 10 centimeters times 5 centimeters equals 10, 100 m times 5, 100 m equals 0.005 square meters. Pressure exerted equals F A equals 5N. 0.005 square meters equals 1000 pascals. B. When the brick is placed on its widest base, area of contact with soil equals 25 centimeters by 10 centimeters equals 25,100 meters times 5,100 meters. Pressure exerted equals F A equals 5N. 0.005 square meters equals 1000 pascals. B. When the brick is placed on its widest base, area of contact with soil equals 25 centimeters by 10 centimeters equals 25,100 meters x 10,100 meters equals 0.025 square meters. Pressure exerted equals F A equals 5N. 0.025 square meters equals 200 Pa. Pressure exerted by liquids and gases. Both liquids and gases exert pressure. Activity. Take a tin can or a plastic bottle. Drill a few holes all around it near the bottom. The holes must be at the same height from the bottom. Fill the bottle with water. What do you observe? Water rushes out from all the holes and falls at the same distance from the can. This shows that liquids exert equal pressure in all directions at the same depth. Activity. Take a tall can, empty talcum powder can. Make 3 holes in it on one side at different heights. Fill the can with water and observe what happens. Water from the lowest hole comes out with the greatest pressure, and hence it travels the maximum distance, whereas water coming out from the highest hole falls nearest due to the least pressure of water. Water from middle hole falls in between. This activity shows water pressure increases with the depth of water. Activity. Take a white transparent glass tube open at both ends. Stretch a rubber balloon to its lower end. Pour water into the tube. You will notice that the balloon bulges downwards. Also note the height of the water column. Pour some more water. Do you see any relation between the amount of bulge in rubber balloon? This activity shows that liquids exert pressure on the base of the container in which they are kept. Now take a vessel with a tap-like opening at its side, or take a plastic bottle and insert a glass tube near its bottom from the side. Tie a balloon to the opening and fill the vessel with water. You will notice that the balloon bulges outwards. This shows that liquids exert pressure not only on the base of the container but also sideways on the walls of the container. This sideways pressure is exerted by liquids but not by solids. This activity shows that liquids exert equal pressure in all directions. This is called Pascal's law. An instrument used to measure liquid pressure is called pressure gauge. The simplest form of pressure gauge is a manometer which measures pressure difference. Gases, like liquids, also exert pressure. Activity. Take a balloon. Inflate it. Leave the mouth open. What happens? The air moves out and the balloon deflates. Take a balloon. Prick it with a needle to make holes. Can you fill air in it? No. The above activity shows that air exerts pressure in all directions and also on the walls of the container. Atmospheric pressure. We have already studied that Earth is surrounded by a layer of air. This envelope of air is called atmosphere. Air is a mixture of gases. Like gases, air also exerts pressure on Earth due to its weight. Atmospheric pressure is defined as the pressure exerted on an object by the weight of the air above it. Air pressure is maximum at sea level. It is about 100,000 Pascal. Air always exerts pressure on the human body because of the tall column of air above us. Do you feel this pressure? No. This is because the pressure of the blood and that of fluids in our body balances out this atmospheric pressure. Otto von Guericke, a German scientist and inventor, in the 1600s, demonstrated the power of air pressure. He joined two hollow, semicircular bolts made of copper of 51 centimeters diameter, and removed the air inside with the help of suction pump. He got a team of 8 horses each to pull each hemisphere apart. The two bolts held together and they could not be pulled apart, showing the enormous force of atmospheric pressure. Air pressure is measured by an instrument called the barometer. It was invented by Evangelista Torricelli, an Italian physicist and mathematician, in 1643. Atmospheric pressure decreases as we go up in the atmosphere. This is because as we go up, the length of the air column decreases and hence atmospheric pressure also decreases. Mountaineers at high altitudes, at times, experience bleeding through their nose. This is due to rupturing of blood vessels in the body due to sudden decrease in the air pressure outside. Horses pulling the hemisphere. Activity. Take a plastic bottle and fill it with some boiling water. The steam coming out of the water will expel most of the air from inside the bottle. After about 2 minutes, screw the cap tightly and put bottle in a trough and pour some cold water and ice on it. As the bottle cools down and the steam condenses, what do you observe? You will see the bottle got crushed. Can you explain why? Since the steam has expelled most of the air pressure inside the bottle is very little. The atmospheric pressure, being greater, causes the bottle to get crushed. Activity. Take a rubber sucker and fit it on a glazed tile. Now try pulling it out. What do you observe? You need a lot of force to remove it. When we press the rubber sucker on the tile, most of the air between the cup and the surface escapes and a partial vacuum is created. The sucker sticks to the tile. Because of atmospheric pressure, you need to apply a force larger than the atmospheric pressure to remove the sucker away. This activity will give you an idea of the magnitude of air pressure. Factors affecting atmospheric pressure. Altitude. As already mentioned, atmospheric pressure is the maximum at sea level. As we go higher up, the length of air column decreases above us, and air also gets thinner. This results in a decrease in atmospheric pressure, ATM. Thus, ATM1. Altitude. Temperature. Air expands on heating and becomes less dense. Thus, atmospheric pressure decreases with increase in temperature. Humidity. As water vapor is lighter than air, humid air is lighter than dry air. Thus, air pressure decreases as humidity increases. Applications of liquid and atmospheric pressure. The pressure at the seabed is much higher than near the surface. This is why deep-sea divers have to wear special suits to prevent their bodies from being crushed. A drinking straw works on the principle of air pressure. When you suck on a straw, you suck out the air in the straw, thus reducing air pressure inside the straw. The higher atmospheric pressure on the surface of the drink forces the drink up the straw to your mouth. A dropper fills by the same principle. When the plunger of a syringe is pulled out, the space below the plunger increases. This reduces the air pressure inside. The higher atmospheric pressure on the surface of the medicine forces the medicine inside the syringe. Jet planes fly at heights where air pressure is very low. Thus, normal ground level atmospheric pressure is maintained inside the plane cabin to prevent bleeding as our blood pressure is much higher than the air pressure outside.